structural realism as a naturalist metaphysical thesis regarding two scientific cases. First, the transition from classical mechanics to non-relativistic quantum mechanics, and second, the transition from classical mechanics to quantum field theory. You at your department probably have heard a lot about Ontic structural realism. Anyway, Professor Lehman is one of the key philosophers in introducing and developing the thesis. Dr. Thébault has advanced the thesis by enriching it with the so-called construction principle in his paper, Quantization as a Guide to Ontic Structure. In this talk, I will further look into the matter and conclude that concerned evaluations confront the Ontic structural realism with some challenges. While some of them may be overcome by choosing just suitable mathematical solutions, some need a revolution in our metaphysics. Now let me briefly outline the talk. My presentation has three parts. In the first part, I will introduce structural realism and its different variants. Particularly, I will discuss how the thesis relates to the problem of representation in philosophy of science. Next, I will argue, following Thébault, that the main thesis of OSR, meaning the world is made of structures, is not strong enough to construe a tenable ontology. Then I will talk about the construction principles already introduced by Karim. In the second part, I will discuss the problem of evaluating Ontic structural realism in the context of two theory changes: the change from classical mechanics to quantum mechanics, and the change from classical mechanics to quantum field theory. I will then show that while the challenge in the first transition may be avoided by a mathematical maneuver, the second one needs a metaphysical strategy. And finally, I would conclude the talk. I would like to introduce structural realism by a well-known example, the Königsberg bridge problem, which is probably familiar to you since high school courses. Königsberg was a town in Prussia. Now in Russia, consisted of 4 separated parts connected by 7 bridges. According to folklore, the question arose of whether a citizen could take a walk through the town in such a way that each bridge would be crossed exactly once. Let's call such a path K-path and its related property K-pathness. The Swiss mathematician Leonhard Euler in 1735 presented a solution to this problem, concluding that such a walk was impossible. Irrespective of how he arrived at the answer, what matters here is what consideration the answer depends on and what considerations the answer is independent of. Particularly, does the answer, meaning having or not having a K-path, depend on, for example, how large are the town's separated parts, or this question that what material are the bridges made of, or this one that are the rivers swollen, high or fast flowing? You are probably agreed that the parts are large does not make the answer yes, and that they are small does not make the answer no. Similarly, the answer is independent of the material of which the bridges are made. Indeed, these are the intrinsic properties of the parts, bridges, and the rivers that K-pathness does not depend on. So we can represent the town with a graph in which these properties are abstracted away. As you see, it consists of 4 nodes or vertices. It contains also 7 edges between the vertices. You see that vertices represent town's parts and edges represent the bridges. But we should also note that while intrinsic properties such as the materials of the bridges or the areas of the town's part are not represented by the graph, the way in which different parts are connected is represented. For instance, having the graph, we can see that there are two bridges between the island, represented by the middle vertex on the left, and the upper bank, represented by the top vertex on the left. In fact, Euler, using this sort of abstraction, proves that Königsberg does not possess the k-pathness property. Now, suppose that all properties of the world are structural ones, like the property k-pathness in Königsberg. In other words, as connectedness in the example is independent of the kinds of components constituting Königsberg, the properties of the world are independent of objects and their intrinsic properties if these latter entities exist at all. Given that, one can encapsulate the essence of OSR as follows. The world is made of nothing but structural properties. This sort of characterization of OSR is in some sense too strong, since it totally excludes the existence of objects and intrinsic properties. Someone may take a more moderate view, asserting that objects exist but are individuated by structural or relational features. Before going further, now is a good time to mention another version of structural realism, meaning epistemic structural realism. Let's recall the Königsberg bridges problem. Someone may claim that perhaps there exist the intrinsic properties of bridges and separated parts of the city, but what can be represented by graph are just relational properties such as k-pathness. Similarly, the epistemic structural realist claims that scientific theories, suitably construed, may inform us just about the structures of the world, whether it has objects or not. So we can characterize ESR by the motto, all we know about the world is what we know about the structural properties of the world. Now the question is how to represent an ontic structure, meaning a bundle of relational properties in the world. In fact, asserting that there exists an ontic structure is not enough. We would like to now recognize it, or put differently, we are needed to represent it. In the case of the city of Königsberg, we represent the concerned structure by graph that you see in the left. But you can represent it with another graph as well. In the graph in the middle, the edges have some differences that you can see. Or consider the third graph in the right, which is distinguished from the first and the second. So in this slide, we have three different graphs that represent the Königsberg problem adequately, meaning by using each of them, we can infer truly that there is no k-pathness property. We don't like such a situation, at least from a realist point of view. In this case, we're faced, at least so far, with a sort of underdetermination, representing a single ontic structure by three different representations. Given that, someone may argue that these different graphs are structurally identical, equivalent, or the same. It's true that the vertices in the three graphs are visually different, but these vertices, as characterized in graph theory, are the same. Then we should consider them and other equivalent graphs as the same entity representing equally Königsberg bridges problem. If we accept such a response, we can handle the problem of underdetermination, since we are finally given a single structure representing the ontic structure. But now the problem is how to present or characterize this final structure associated with different but equivalent representations. How can we abstract away this new entity from the older ones? This situation is not unusual in mathematics. Mathematicians deal with different but structurally equivalent structures as a single entity. In fact, they define an equivalence clause which its members are in an equivalence relation, the relation that is symmetric, reflexive, and transitive. They then pick out a member of that clause as a representative member and then work out with that to define their concepts and prove their theorems. For them, there is no difference between this or that member to be the representative member. All members of an equivalent clause are the same or equivalent. As you see, the equivalence clause depends on the equivalence relation. So if you define two different equivalence relations on a single set, it's possible that you get two different equivalence clauses. Indeed, it is the context that determines which equivalence relation is suitable. For example, in topology, all homeomorphic topological spaces are the same. Or in differential geometry, all diffeomorphic differentiable manifolds are conceived of as a single structure. Putting aside some problems like whether these sorts of classes are foundationally well defined or not, or this worry that this treatment opens the door to intentional actions of cognitive agents in representing ontic structure, what matters here is that we deal with a class of equivalent structures, not a single one. As you see, if we denote an equivalent class by S, we are finally committed to submitting that it is S that represents the ontic structure R. My approach introducing structural realism and OSR was upside down, meaning that theses were introduced without mentioning the rationale behind them. But why should we replace the traditional metaphysics with OSR that is very removed from the phenomenal world? After all, the world we perceive contains objects and their intrinsic properties. I didn't narrate the story of structural realism chronologically. At least modern literature on this kind of scientific realism was produced as a response to the two challenges to scientific realism, meaning the pessimistic meta-induction and metaphysical underdetermination. However, both challenges may be overcome by OSR. The ontic structural realists respond the former argument by saying that preceding and succeeding theories in the history of science are structurally related, though the objects and the properties they refer to are completely detached. Concerning the latter argument, she says that different empirically equivalent theories portraying different worlds have a shared structure. So it is the common or shared structure between preceding and succeeding, or between underdetermined theories, which to the scientific realists should be committed. What I've said till now concern the basic of OSR. Now the question is whether OSR can immune structural realism from the problem arising from the pessimistic meta-induction and metaphysical underdetermination. Indeed, there is no a priori guarantee, since there may be no shared structure between given preceding and succeeding or between underdetermined theories. For example, exploring the theory change from Newtonian mechanics to the theory of general relativity, there may be no shared structure. In this sense, OSR is a naturalist thesis which may be confirmed or disconfirmed by genuine cases in science. But this feature of OSR, meaning the ability to scientifically be evaluated, is not restricted to the existence of the shared structure. Even if such common structure exists, it is quite conceivable that the physical content of different theories is detached from the shared structure. As such, the shared structure is not substantial enough to construct a structural ontology. Actually, we need such a relation between the shared structure and the empirical content of theories. Otherwise, we cannot use the no miracle argument for scientific realism. Upon the argument articulated within the framework of structural realism, the best explanation for the success of a theory is that the underlying structure of the theory represents an ontic structure. But if we don't care about the relation between the common structure and the empirical content, we cannot explain the success of constant theories in terms of the common structure, which too we are ontologically committed. But OSR per se does not say anything about such substantialness. To better understand the meaning of substantialness, let's consider another simple example. Consider a physical situation regarding the motion of a car, which is supposed to be described by two preceding and succeeding theories. The velocity and acceleration of the car in some places of the path decrease and in some places increase. Now suppose that the underlying structure of preceding theory is a circle and the underlying structure of the succeeding theory is the square. These are for the sake of simplicity. According to Ontic structural realism, the circle and the square have a shared structure which represent the related ontic structure. Appealing to the topological features, the structural realists would say that these two representations are homeomorphically similar, meaning, roughly speaking, by deforming the square without cutting it, we can get the circle and vice versa. So the succeeding theory inherits the topological structure underlying the preceding theory. Indeed, there exists a structure between the two theories. But is that enough? It seems not, since the topological structure does not represent kinematic and dynamic properties in the physical situation. For instance, this structure cannot explain or predict when the car would accelerate and when decelerate. In other words, the topological structure is not substantial enough to be appealed by the structural realists in portraying the structural reality. So we are needed to add some constraint on ontic structural realism to be a viable ontology. They are the construction principles which Karim has already developed in his paper Quantization as a Guide to Ontic Structure. One of these principles may be called the substantialness principle, upon which these structures, meaning common structures, must be substantial enough to constitute a viable alternative ontology. Now the question is whether common structures, whatever the given theories, may have some general features such that having them makes the common structure substantial enough. Unfortunately, there is no such a rule, since the dependency of empirical content on the underlying structures varies from theory to theory. Therefore, how can we be sure that OSR incorporates the principle of substantialness? The story goes like the issue of existence of common structure. As in the case of existence of common structure, a priori, we do not know that whether the given preceding and succeeding theories have a shared structure or not. In the case of substantialness, we do not know a priori that the existing structure is substantive enough or not. So there is no a priori guarantee of it. We should do the job a posteriori. In fact, we should consider a genuine case of theory change or ontological underdetermination, construct a structural presentation of given theories, see whether they have shared structure or not, and finally determine whether these structures are substantive or not. If yes, OSR is confirmed, and if not, OSR is disconfirmed. It seems to me that This makes the structural realist project as a naturalist scientific one that may be challenged by new cases. The scientific theories may be questioned by new empirical data. Besides the issue of substantialness, there is another challenge which potentially threatens OSR. Suppose that through the change from the preceding theory A to the succeeding theory B, there exists more than one common structure which do not belong to a single equivalence class. If so, we find ourselves confronted by sort of a structural underdetermination, meaning that there are two incompatible structures which may justifiably be used to represent the world. In the next, we will see that such kind of underdetermination arises in the theory change from quantum mechanics to non-relativistic quantum mechanics through geometric quantization. This problem may be emerged in the case of ontological underdetermination as well. It's possible that two underdetermined theories share more than one common structure. If there is no equivalence relation between these common structures, then we cannot describe the related ontic structure uniquely. So we are required to add another constraint upon OSR. The structures used to avoid the two arguments, meaning metaphysical underdetermination and the pessimistic meta-induction, must be consistent. The points concerning a posteriori evaluation of the consistency go like the substantialness, which I pass over. Now let me begin the second part. In this part, I will discuss the two cases of theory change, the transition from classical mechanics to quantum mechanics and the transition from classical mechanics to quantum field theory, to see whether ontic structural realism enriched with the construction principles would be corroborated or not. Let's look at the different steps the ontic structural realist should take in the case of the theory change in the case of the first theory change. The first and second steps are reconstructing classical mechanics and quantum mechanics within a suitable mathematical or mathematical framework, like set theory, category theory, etc. After formulating the given theories in the suitable mathematical framework, the structural realist should find an appropriate relation, maybe induced by a desired map between the two reconstructed theories. But this relation between classical mechanics and quantum mechanics, which is reasonably induced by a map, are taken to satisfy two sorts of conditions. The first group are physical ones. The second group relates to the construction principles. The candidate relation is a map between the set of smooth functions on manifold M and the set of self-adjoint operators acting on Hilbert space H. The first set represents classical observables and second one represents the quantum mechanical observables. This map, denoted by Q, is supposed to satisfy 5 physico-mathematical conditions. The first one is that Q is linear. According to the second, Q1 equals I, where 1 is the constant function and I is the identity operator. The third condition shows how the commutativity of classical observables relates to the non-commutativity of quantum mechanical observables. The fourth condition ensures that a polynomial of function gets mapped into a polynomial of operators. And finally, the fifth condition, the assumption of reducibility, asserts that The Hilbert space should be small enough such that momentum and position operators act irreducibly on H. This assumption is needed for the Stone-von-Neumann theorem, which I will discuss shortly. In the next step, we should explore whether the shared structure characterized by the map is both consistent and substantive or not. But unfortunately, there are several no-go theorems showing that there is no any map satisfying physical conditions together. So considering the construction principles is out of the question. To compensate for this shortcoming, there are two mathematical solutions on the table. The first one is the geometric quantization or GQ program. In this procedure, someone tries to define a Hilbert space and its associated operators via the notions already present in the formulation of classical mechanics in such a way that the non-commutativity of quantum observables is satisfied. The second one is the formation quantization, upon which people do not appeal to any Hilbert space, but try to formulate classical mechanics such that the non-commutativity of quantum observables arises through imposing a limiting condition. In what follows, I will describe these quantization programs in turn. First, geometric quantization. GQ is a mathematically complex machinery having various phases in which many differential geometric concepts are used. In what follows, I will introduce the program just schematically and focus on its three main steps, out of which a sort of structural ontological underdetermination arises, and then the consistency principle is violated. The first step is constructing or defining a Hilbert space through the differential geometric notions which already exist in the structure of classical mechanics. This step is called pre-quantization. The Hilbert space defined in pre-quantization, however, cannot be considered as the final quantum space, since the map which is defined between a smooth function and the set of self-adjoint operators does not satisfy the fifth condition. So we should take another step, which is called polarization. In this stage, we try to restrict the old Hilbert space by intersecting it with another space in such a way that the fifth condition is satisfied. But by doing that, a new problem arises. In fact, at least for some cases, the space intersected with the old Hilbert space is not square integrable. To handle this problem, we need a new measure of a new Hilbert space. These new concepts are defined in the third step named the construction of half-form Hilbert spaces. It can be shown that the desired map between the smooth functions on M and the self-adjoint operators acting on this new Hilbert space satisfies all 5 physical conditions of quantization. But what about the construction principles? The Ontic structure realists unfortunately cannot appeal to GQ to corroborate OSR because, firstly, final half-form Hilbert space, HH, depends on polarization. Secondly, there are different polarizations. So thirdly, there are different final Hilbert spaces. And more importantly, the transformation between two Hilbert spaces associated with two different polarizations are not necessarily unitary. Therefore, as conclusion, there is no single equivalent equivalence clause to be considered as a common structure between classical mechanics and quantum mechanics. And it is nothing but a violation of the consistency principle. Given that we are confronted with a sort of bifurcation, as the first option, someone may conclude that this case shows that ontic structural realism is not a good metaphysics, since in the transition from classical mechanics to quantum mechanics, there are different shared structures which are incompatible. So having them, we cannot determine uniquely the ontic structure in question. Therefore, OSR has been a posteriori disconfirmed. But there is another option. Someone may argue that the supposed disconfirmation arises out of the geometric quantization program. Likely, in other methods of quantization, a consistent structure to be found. This option, as it is, does not confirm OSR, but just saves it to be demolished. The solution is mathematical, since it suggests another method of quantization. In the following, I will explore deformation quantization, or DQ, as the alternative candidate. However, someone may accept GQ, but avoids the inconsistency by adopting a new metaphysics for different common structures which are supposed to be inconsistent. I will say more on this option in the case of the transition from classical mechanics to quantum field theory. But now let's see what is DQ. There is a core idea behind DQ. In DQ, we do not deal with two sorts of structures, meaning a commutative one associated with classical observables and a non-commutative one associated with quantum observables. In DQ, we deal with a single structure that is non-commutative per se, but in the limit, as h bar approaches zero, meaning in the realm of classicality, it becomes a commutative one. Now let's see what are the components of DQ. Like GQ, DQ has a complicated machinery consisting of different steps, which their details cannot be spelled out here. The first step of DQ is presenting classical mechanics within the framework of symplectic geometry. The structure resulted in this step has a commutative algebra, and it's called the structure of classical mechanics, or SCM. In the second step, named formalizing or formalization, we embed a formal indeterminate, say H bar, into SCM. The machinery that is used is the formal series framework. We call this latter structure the formal structure of classical mechanics, or FSCM. In the final step, called the deformation step, we define a new operation, meaning a star product over new formal smooth functions coming from the second step. The star product converts the commutative algebra to the non-commutative of smooth functions. We call the new structure that embeds the star product and shows a non-commutative algebra the formal structure of classical mechanics, or DFSCM. So there are three kinds of structure: SCM, structure of classical mechanics; FSCM, formal structure of classical mechanics; and the formal structure of classical mechanics. Now let F and G be two smooth functions. It can be shown that the non-commutative algebra over smooth functions, which is induced by star product leads to a commutative algebra reified by Poisson brackets. More precisely, the limit of f comma g in a square bracket, which is non-commutative due to the star product, over h bar as h bar approaches to 0 leads to f comma g in Poisson bracket that is commutative. In this sense, the transition obtains. Before examining DQ to see whether it follows the consistency principle or not, it is a good time to compare DQ with other methods of quantization and their relations to OSR. Given other methods of quantization, the Ontic structure realist would say that classical mechanics and quantum mechanics attribute different structures to the world. These structures may have a shared structure represented by a functor held between the category of classical functions and the category of quantum operators. But given DQ, she would say that the world has a single structure represented by DFSCM. However, DFSCM per se is non-commutative, but in the limit h bar approaches 0, it becomes commutative. So this is the difference between other methods of quantization and deformation quantization. But I think that it's a big difference between DQ and other methods of quantization. But what about the consistency principle in DQ? Does DQ meet this condition? More precisely, the question is, does there exist, given an SCM, a unique DFSCM up to an equivalence clause? If there are more than one DFSCM, then we should attribute different structures to the fundamental ontology of the world that is nothing but a sort of structural underdetermination. This case, if occurs, makes the situation of DQ similar to that of GQ. In fact, they are both violate the consistency principle. But there is a good news here for the Ontic structure realist. In fact, the Kontsevich formality theorem ensures us that there exists just one non-commutative structure to which the Ontic structure realist should be committed. According to a corollary of his formality theorem, there exists a one-to-one correspondence between the equivalent clauses of FSCMs defined on an SCM and the equivalence clauses of DFSCMs. So the DQ program, due to Kontsevich program, respects their consistency principle and finally provides support for OSR. This is where the story of OSR and the transition of classical mechanics to quantum mechanics ends. But there is an important issue here that should be noted. The formality theorem holds just for systems with finite degrees of freedom. In other words, the existence and classification is not guaranteed for the theories dealing with infinite degrees of freedom. In fact, the formality theorem does not work philosophically for the transition from classical mechanics to quantum field theory, since the transition deals with physical fields which have infinite degrees of freedom. So we should consider separately this latter theory change. For the sake of simplicity, recall the initial scheme of quantization, which was based on a map between a smooth function on manifold M and operators acting on the Hilbert space H. This map here is denoted by W, which its range is set of unitary operators. Putting aside other mathematical details, the final results of mapping are structures. named the representation of while relations, which represent quantum systems. Two representations are physically equivalent if there exists a unitary transformation between them. Now the question is whether in all cases there exists such a transformation. In other words, are all representations associated with a single transition always equivalent? This von-Neumann theorem guarantees the existence of such a transformation, but just partially. More precisely, it asserts that for any linear finite dimensional symplectic manifold, all weakly continuous irreducible representation of while relations are unitary equivalent. Putting aside the mathematical details, in the theorem, what matters here is the condition of finiteness. In fact, it corresponds to the formality theorem, which holds just for finite systems. Given that, we accept arising a sort of structural ontological underdetermination in the transition from classical mechanics to quantum field theory. In fact, in the transition from classical mechanics to quantum field theory, involving a system with infinitely many degrees of freedom, unitarily inequivalent representations emerge. But it is a case for the violation of the consistency principle and then against Ontic structural realism. So we are once again faced with a sort of bifurcation. Is confirming OSR a posteriori or corroborating OSR by a mathematical solution which does not exist, or adopting a metaphysical resolution? Probably you guessed that the metaphysical resolution, like other situations in which one faces a sort of inconsistency in her metaphysics, is based on adopting a sort of modality. Having this kind of metaphysics, we can say that the world contains incompatible entities, but in possible modes, not actual ones. Stephen French has suggested a sort of modal ontic structural realism to overcome the problem of structural ontological underdetermination emerging from unitarily inequivalent representations. To see it, an example may be helpful. Consider a flexible rod which stands vertically on the table. When you apply enough force on the top of the rod, it bent and took a certain orientation. In fact, by applying the force and bending, it loses its first rotational symmetry. This phenomenon is called symmetry breaking. What matters here is that the rod can take different, indeed infinitely many orientations to be bent. So there is a space of possibilities which may be attributed to symmetry breaking situations. A certain kind of symmetry breaking occurs in systems with infinite degrees of freedom. For instance, consider a ferromagnetic material whose magnetic dipoles upon the Curie temperature are randomly directed. System in this condition has a rotational symmetry. But below the Curie temperature, the symmetry is spontaneously broken down and magnetic dipoles are aligned to a direction. But like the previous example, there are infinitely many directions toward which magnetic dipoles can align. This sort of phenomena, which are described by quantum field theory and quantum statistical mechanics, is called spontaneous symmetry breaking. Now we can consider unitarily equivalent representation as representations of these possibilities. According to French, then the ensemble of unitarily inequivalent representations represents the set of all possibilities in the world. Possibilities like post-break situations. Now, let me summarize the talk. OSR enriched with the construction principles are put to the test in two cases. The first case is the transition from classical mechanics to quantum mechanics. We saw that in the transition prescribed by geometric quantization, the consistency principle is violated. But in the transition described by DQ or deformation quantization, the consistency principle is followed. So the Ontic structural realist can appeal to DQ to construct a viable ontology. The second case is the transition from classical mechanics to quantum field theory, in which the systems with infinitely many degrees of freedom are involved. As we saw in all transitions prescribed by all methods of quantization, the consistency principle is violated. So the problem cannot be handled mathematically. To remedy the defect, the Ontic structural realist should adopt a modal metaphysics. Thank you for your attention.
That was a really fascinating, very rich talk. Thank you very much. I really, really appreciate it. I have many, many questions, but as is normal, what I would suggest is that the students go first. And I think probably given we have a small group, ideally if you could switch your cameras and mics on and ask the question, but I'm happy to read out questions if you put them in the chat as well. So we can have a little bit of a break, but do any of the students who wanted to ask a question, if you put Q in the chat, I can make a little a running list.
Excuse me, question will be on chat or will be said?
It's okay. I can ask the questions. Should we stop the recording though, actually, as well?
Yeah.